Oh yeah, I've not got a link to your website either, Matt,
That's probably for the
because
best.
because I forgot.
All right. I think we can get started. I'll start admitting people as they kind of come in. And yeah, so if you need anything, just let me know. I'll be here, and Paul, you can take it away.
Fantastic. Well, welcome everyone. I'm really excited this year, so it's really hard to tell because I can't see all of you, and I can't do any audience participation, which is deeply frustrating to me. Because what I want to ask is how many of you have been here before, and how many of you have tried Flame GPU? I suspect that a few of you have, and probably for the last 2 years, if you've been to this tutorial, I've alluded to the fact that there is something new and exciting coming called Flame GPU2. And I'm really excited that this is the first kind of outing for it. This is really new, so we're not even quite at alpha release yet. So everyone here is somewhat of a guinea pig. The code is reasonably stable. We have tested it, although there's some magical code pixies still working away in the background, just making sure things are all going to run smoothly in half an hour when we actually try out some code. But this kind of latest version of Flame GPU addresses a whole number of issues that the first one had. And it's been almost 3 or 4 years in the making, so it's quite monumental that I can talk about it for the first time today. So what we're going to be talking about is large-scale agent-based modeling with Flame GPU2. Where's my last one? There we go. So all of you know about agent-based modeling. For those that don't do agent-based modeling, it's a way of expressing an individual or expressing individual behavior and then performing simulation that allows those individuals to interact together and usually produce some form of emergent behavior. So something which is greater than a sum of the individual parts. So we see great examples of agent-based modeling, things like crowd simulation. Complex systems such as the brain can be simulated by simulating individual neurons. And something that's pretty common across all of these types of agent-based simulations is the computational challenge that is required to kind of solve them. So where you have lots of individual things, they generally have some kind of internal state, whether it be variables or some form of internal representation. It needs a lot of computation to continually update those, either according to events or according to some kind of discrete time step. And this computational burden means that the scale of things that can be simulated is quite often limited, or it means that the exploration that you do around the model can be sometimes constrained by this limitation. I've seen some great examples of agent-based modeling recently with kind of COVID modeling, and it's no surprise that some of the issues they have around performance and scaling those to kind of much larger systems or running much larger numbers of conditions. So the area of work that I focus on, or at least one of the areas of work that I focus on, is this idea of applying GPUs. So GPUs are graphics processing units. They take the idea of kind of multiple cores to the extreme. They can be kind of described as a many-core architecture. They're fundamentally just a piece of silicon, exactly like a CPU, but they are designed with this idea of high parallelism. And because they are, it means that it implies certain things. So it makes them a little bit more difficult to program. It means that your programs need to be expressed in a highly parallel way. But if you're able to do that and utilize the hardware to its kind of its best extent, then you can get an enormous difference in terms of raw compute performance than you would on a traditional CPU architecture. So the idea behind the software, Flame GPU software, is to make that process simple. Yeah. So in terms of a GPU, the way in which it's programmed is this idea of kind of data parallelism. So it's not thread-based parallelism like you might get in a CPU, where you've got multiple things doing different things. So you've got Word running and some programming running and some Python running somewhere, and that they're all kind of independent. It's this idea of a data parallel kernel. So what that means then is that we have the same program applied to different data. So it could be something like applying a simple piece of linear algebra to a different piece of data, or it could be something much more complicated. And it breaks it down in this way that then allows you to express a data parallel kernel or a data parallel program, and then that's applied over a stream of elements over a set of data. Behind the scenes, that's mapped transparently onto GPU cores, but that's the kind of constraints that we have to work with when developing a GPU program. So the question that I always ask, and some of you may have been to this tutorial before and seen this slide, this kind of introduction slide, but GPUs then, highly parallel, but so are multi-agent systems, right? So if I have n GPU cores, you know, a modern GPU has many thousands of cores, will it run my agent-based simulation n times faster? And the answer, of course, is almost certainly not. So although a multi-agent system has got lots of individuals which can be simulated independently using this data parallel method, there are also other aspects that restrict the ability of the GPU to kind of increase performance. So particularly there's this kind of growing list of things. So first of all, there's no unified parallel model of an agent. So many models are built using the idea of kind of serial principles. So models like Sugarscape rely on the fact that each agent operates sequentially in turn to avoid things like people occupying a shared resource and having some kind of conflict. So agents are also kind of heterogeneous, right? So the more complex the simulation, the more true this is. So if you consider something like a biological example, modeling cells, you have cells in different states. And during those different states, they perform different behaviors. So this breaks this idea of single program, multiple data, because agents in different states have got different programs. Agents are also born and die, so this potentially leads to sparse data layouts. Again, this is problematic for GPUs, so they need compact data representation to be efficient. And agents communicate, so agents don't just independently operate, they obviously communicate with other agents, and that means that we need to have some form of kind of thread-safe mechanism for them to interact that's hopefully avoids race conditions and permits kind of reproducibility of experiments. Agents don't stay still, they move around, particularly when they wanting to communicate. They may interact within a particular spatial radius, for example. So we need to be able to build data structures that allow that to happen. But we need to build those data structures using these constraints of a data parallel programming model on the GPU. And as I said, GPU programming is hard. So if we try to solve all of those problems for our agent-based simulation, it's incredibly difficult given the programming model and the expertise required. So this is where Flame GPU comes in, particularly Flame GPU 2. So the idea, just as with the original version of Flame, is to abstract this complexity of the parallelism and GPUs away from the modeler. So you shouldn't really need to know that you're using a GPU at all to use Flame GPU. We should be able to, as modelers, spend our time doing modeling and let the GPU take care of the heavy lifting and the performance and all the algorithms at the back end. So Flame GPU 2 differs slightly from Flame GPU 1 in that we've got rid of some of the way in which you would express your model. So Flame GPU 2 is API based. So there's a simple API for expressing a description of a model. And a description of a model has an agent, it has messages, which are things that are communicated between agents, it has functions, which represent the behavior of the agents, and it has an environment which provides a description of certain things that remain constant for all agents. We've got rid of XML in Flame GPU 2, so no longer do you have to describe your model in that kind of long verbose XML format. A simple object-oriented API which allows you to describe your model. There will be some backwards compatibility, so if you desperately still want to describe your model in XML, you can, but one of the complaints that we've had in the past is that it's a little bit awkward having to necessarily do that. For Flame GPU 1, it was necessary because everything was code generated. So from your XML model, we generated GPU code. With Flame GPU 2, everything is wrapped behind an API. So there's no need to do code generation in the same way. Behind the API then, there are all kinds of implementations that resolve some of those common problems that I described, things like communication, data structure building, sparse representation. That's all hidden away behind the scenes. All of the mapping to and from the GPU device is taken care of. And likewise, interactive visualization is provided so that you can either visualize your models in terms of things moving around on the screen, or you can run them non-interactively and produce log files that represent the output state of the simulation. What I was desperately hoping was that we would be able to have a Python version of Flame GPU2 available. We in fact do now have a Python version of Flame GPU which works. I'm 99% confident that it would work for everything that's in the tutorial, but it's unfortunately maybe about a week away from a point that I'd be 100% sure that it would work. So we will be using the C++ API, which is the kind of the underlying API in which the Python version is wrapped around, but it does mean that there will be a Python API for developing GPU agent-based models very, very soon. So the way in which we describe agents within Flame GPU is using this formal model of agent interaction. So it's a formal model because it's based on a form of state machine called an X machine. So this representation is particularly nice because it expresses kind of an inherently parallel abstraction. So if we consider a very simple simulation, one in which we have a number of agents that want to communicate with each other and then move according to some information that they've gathered. So this could be something like a Boyd's type of model, so a model of flocking, or it could be some kind of simple cellular behavior. The way in which we would express that interaction with the state-based representation is that we would specify, first of all, the communication, in this case, a location message, and that's represented in this kind of green box that you see on the screen. We then have to represent the different functions of the agent. So one of the functions is send locations, and that will output a location message. The next function is then read those locations. The final function is move, in which we're going to respond to the location messages which we've gathered. By breaking the messages up into this way, we introduce this idea of layers. So we have 3 layers in this example, and that means that we have the opportunity for kind of implicit synchronization between each layer. So it means by the time any agent in parallel is performing the read locations function, there's a guarantee that the send locations function has been completed by all agents, and that the location messages all exist. And this is one of the mechanisms which is used for helping to kind of schedule things onto the GPU device. But that was a relatively simple example. This is a slightly more complicated example of the European economy. We have some similar complex examples that are currently part of EU projects, modeling things like the immune system, which again produce quite complex graphs of behavior. So just a bit of a refresher as to kind of Flame GPU1. So Flame GPU1 used this kind of mechanism of describing your model using a model file, describing some behavior scripts, and the template. So we had a number of templates that then generate simulation code written for the GPU device, which could then be compiled and linked against your behavior scripts. So that's somewhat simpler now for Flame GPU2. Optionally, you could describe your model using a model file, and what in fact that would do is translate to a number of calls to the modeling API. So there's almost a one-to-one mapping between the old XML model file elements, such as agent, message, and API calls, such as new agent, new message. Now, everything's contained within one file, so you describe your model using the objects from the API. You describe your agent functions within the same file. All of the what was in templated codes is now wrapped up in the Flame GPU2 library, which has a header file for accessing kind of all of the objects that you need for describing your model. It can be linked and built similarly with visualization or kind of output files. We do still have the optional kind of XML input files, which can be used for describing kind of the initial state of agents, or you can procedurally generate agents as part of your model kind of initialization and use the XML input file just for putting things like environment variables. So I'm going to move on to giving a simple example of how we kind of describe a model in Flame GPU. So this is about the most simple model that you could have in Flame GPU. It follows that principle of the simple model which I showed earlier. This model's a benchmarking model that we have called the circles model. So effectively, every single agent has got a repulsive force and an attractive force. And what happens is when we run the model, obviously things will try and move together, but they form kind of these kind of spheres by balancing the kind of the attraction and repulsion that they have. So that's what the model looks like. And this is how we go about describing the model. So the diagram that you can see is the hierarchy of objects that we have available for the Flame GPU2 API. First thing that we do is we create a model description, and that's what it looks like in the bottom box of your screen. Describe a model object. So the next thing that we do is then we go on and describe the messages. So a message is described using the kind of the syntax that you can see again on the screen there. We have this differentiation between different types of message. So by default, things are called, so by default, sorry, we have a brute force message. The brute force message simply means that when an agent is going to read that message, it will use a brute force technique of reading every single message that is in that list. So any agent at any point in the simulation step has output a location message. Then when that message is read, an agent would have to read every single one of those. So the syntax of creating a variable for a message, and a message is just a collection of variables, a collection of information that will be communicated. It's very similar to the syntax that you'll see for other aspects of Flame GPU2. So it's using C++ templating to define the type of that message, and then we give it a specific name. So this message has got an ID variable, which is of type int, and it's got an X, Y, and Z variable, which are of type float. Simply just represent the position of the agent in the environment. So the next thing we must do then is describe the agent. So again, very similar to a message, an agent is really just a collection of variables. These variables are going to change over time according to the behaviors that we specify. But our simple circle agent has got, again, an ID, X, Y, and Z position. It's got an additional value called drift, which we actually store for doing some validation, and it has a couple of functions. So it has an output message and a move message. In this case, we haven't specified an input message function. We've combined the input message and move functions together. And what we do with each of those functions is we set a property that says whether or not it inputs or outputs a message. Obviously, output message is going to output a location message, and input message is going to input a location message. That then means that when we define the behavior of that agent, we will be able to kind of pass through those message loops or output to those message loops. So next thing we need is a simple environment. We can create an environment description directly from the model, and we can add certain variables to it. So we can have a global repulsion factor, a global radius. So these are kind of constant variables that any agent can have access to during any particular agent function. And that means then that we could perhaps change those as part of our initialization script if we were to do some kind of inference or do some exploration of our model to see what the impact may be. So next we need to see what an agent function actually looks like. We've described what the agent looks like in terms of the fact that it will have an output message function. Well, this is the actual description of the output message function itself. So it has this reasonably simple syntax compared to the original Flame. The number of arguments for that function are greatly simplified. There's now 3 required arguments. The first is the agent function's name. The second is the input message type. And the third is the output message type. So obviously for the output message function, there is no input message, so we use this default of message none. If the function was not performing any message input or output, we'd use message none in both cases. But in this case, we know that the message output type is of brute force. So for any agent function, we always have this kind of Flame GPU singleton object, which is available. And that singleton object on the device has got a number of things that we can do. So we can do things like message out, and we can set the variables for that particular message. If we were to try and set a variable that didn't exist because our message description didn't have it, it would give us a runtime error. And the very final thing that we do is, in this particular case, we return an agent state, which says that the agent is still alive. So any agent function, it's possible to kill the agent, and all we would do there is return agent dead if that was the case. So here's a slightly more complex function then. So this represents the move function. As you can see, it's doing a little bit more. It's still relatively simple in terms of the description, but what we can see is on line 3 and 4, if I move my mouse around, you should be able to see that. On lines 3 and 4, we're actually getting the repulsion and radius value from the environment. Again, it's accessed by this Flame GPU singleton. We're also getting the local an individual agent's variable by saying Flame GPU get variable. So this is returning a single variable for that agent. And then we have a range-based for loop, which allows us to iterate through the message inputs, get variables from the particular messages, and although there's not enough room on the screen to put the full function in, we can do some form of calculation between the message positions and the agent positions to calculate a distance, which we can then update at the end of the agent function. So we've got messages, which is information. We've got agents and functions, which is the description of the individuals and their behaviors. We've got environment that describes some kind of common environmental properties. The last thing to do is to describe the execution model. So this is the interaction model, if you like. The way that we do this then is that we describe a number of layers. So this describes our kind of the scheduling of the agent functions. Have to be slightly careful because obviously we wouldn't want to have the move function before the output message function, as this location message list would be empty. But what we do is we then specify the execution order, if you like, of each of the agent functions. If we had multiple agents, we could schedule multiple functions within the same layer if they were independent of each other. They'd be independent if they didn't rely on some form of communication or message. But this allows us to then build up our kind of our execution model that represents a single iteration of the simulation. So what will happen when we run the simulation for a number of steps is this same process, this same loop will be run through a number of times that we specified, or until some exit condition is met, and that constitutes our kind of full simulation. The other thing that we've done here is we've added a step function. So both initialization step and exit functions are not agent functions, they're simple host functions that allow us to perform kind of bits of useful code that could occur on the host. For example, a step function performs some validation. The validation function, this validation is just a function pointer, but it allows us to check, say, the drift to make sure that it is not approaching some value that would be abnormal for this model. We'll see an example of the step function in the slightly more complicated model that we use in the tutorial example. The very last thing that we do then is with the model, that's a complete model description. We then need to instantiate that model on the GPU device. To do that, obviously, we need to specify a set of initial agents. That could come from an input file, or we could dynamically specify what those values would be. In this case, we're going to specify dynamically what those values would be. So we create a CUDA agent model from the model description. The model description contains all of the things that we had previously just defined. We're going to use some existing C++ libraries for generating a random distribution. We're going to create a population of a particular type of agent. In this case, it's called our circle agent. We're going to loop through the number of agents that we would like and create a new instance of that agent. We're going to set the variables of that agent to random numbers, and then we're going to set that population as the initial population of the model. So behind the scenes, this is going to move everything to the device. It's going to compile and all of the kernels that are required, configure the model so that it can execute in parallel, so that when we issue the command CUDA model simulate, it's gonna run all of the model. Now, if we had visualization mode enabled, then we'd get that same visualization that we saw at the beginning. Otherwise, the default behavior is that we would export the final states of the agents using this command at the end, export data. We'd export the final states of the agents to a file. So just quickly, I want to show some examples of the types of things we can now do with Flame GPU. So a lot of these are from Flame GPU 1, but the examples have been ported over to Flame GPU 2. So we can do things like game of life. We have quite complex biological cellular examples. And this one's quite an old one now of epithelium tissue growth. The immune system model that we have is much, much more complex. It's many thousands of lines of modeling code that produce a great deal of GPU code, actually. We can do things like crowd simulations. Again, this is a simulation around the Olympic Village. It's quite old now, this simulation, but we're continuing various different modeling projects that we have here in the UK, looking at simulation of crowds and vehicles. I should be able to, no, the video is not going to play, but that previous example there is a model of micro simulation of vehicles moving around a road network. So that kind of completes the formal presentation aspect of this tutorial. But this is a hands-on tutorial, so everyone's going to get a chance to have a play with Flame GPU and with a particular model. So the way in which we do that is we've got a Jupyter notebook that will kind of hold your hand and guide you through the process. Don't worry, you're going to get free GPUs. The way in which you need to do that is you need to go to this Google form and tell me what your email address is. You then use the same email address to sign up for this Instance Hub website. It's a site that I've created for sharing GPU instances. Sign up with the same email address and then you'll have access to this particular lab. I'm quickly going to show you what it looks like to run that lab, but it will start up and you'll just have to click a button and it will launch the Jupyter notebook that you can then work through. The way it can then work in the room is if you've got any questions, you can kind of raise your hand, and if you need if it's just a simple question you can ask in the room, then you can ask it in the room. If you would like kind of a bit of one-to-one help, so you want to sort of look at what it is that you're doing, answer some questions, then we can move into a separate breakout room and either me or my colleague Matt will help you to do that. So I'm just quickly going to show you what this looks like. So once you sign up for Instance Hub, you will see under My Labs, you should get Flame GPU2 tutorial. You click participate, then you'll have a button here that says connect. So I've already connected to this one in advance. I've got a Zoom thing in the way of my screen, so I can't see. There we go. I've already connected to this instance. Effectively, what happens when you click connect is you'll have to wait for approximately 2 minutes for the instance to spin up in the cloud. You'll then be provided with some connection information. Once it's finished connecting, you can click on this notebook link here and it will open up the Flame GPU tutorial notebook. There's a description of everything that you need to do to kind of follow the examples. What I would say is once you've started up, make sure you run this command first. This is going to take roughly 3 to 5 minutes to build the library, which is the first thing that needs to be done. And whilst that's building, you can have a read through the description of the model that we're going to use for the tutorial. Hopefully by the time you finish reading that, the library will be built. The library only has to be built once. When you subsequently want to build your model, it only needs to link against the library, so that's a one-time thing that needs to run. But you can run individual cells just by clicking the run command here. Okay, so I guess before I encourage you to begin undertaking the exercise, does anyone in the room have any questions at this point? Stop sharing my screen.
I think there's one question in the chat.
Okay, yeah. I'll stop sharing my screen so I can see that now. So you didn't catch the URL. So would you mind Juniper, sharing that single slide that I sent, and then
Definitely.
and that's got all of the URLs on there. But so if you go to www.flamegpu.com/tutorial, then all of the links that you need are also on the tutorial page as well.
Desktop 1, desktop 2. Okay.
Okay, excellent. So I'm just going to wait for just a couple of moments, just whilst people are filling in that that form, because I need to manually copy those over onto Instance Hub in a moment. So I'll just wait for people to have a few moments to do that. Please do feel free to kind of shout up if you've got any questions at this point.
And can you see my screen okay?
I can't see it actually. It says ALife lecture hall B host has started
Oh, I'm
sharing.
probably sharing the wrong screen. Sorry. Let me get out of there.
I can see responses coming in now. That's great. So once you've filled that form in, I'll kind of copy those email addresses over onto the lab so that you've got access, and then you'll need to sign up to Instance Hub.
Silly screen. Yes. Oh, there we go. Haha. Okay. Can you see it now?
I still can't, but
No, it's still black screen.
it just says ALife lecture hall B host has started sharing a screen.
Weird. Huh. Okay. Let's see here. Stop sharing.
So I can see that someone says that they have to disappear. That's absolutely fine. If you do want to take part in this tutorial, so if you want to undertake the exercises, I've made this lab available.
Oh, I see.
So as long as I've got your email address, I can add you on, and this lab will run for the whole of the conference. You get two hour sessions on the GPUs to undertake the lab. So you know, you can have a go now, and perhaps if you want to have another play later, you can. If you need a bit more than that, then please just email me directly or reach out to me on Slack, and you can get access as well.
Hey, Paul, can you stop sharing your screen? I think that's why it's.
I don't think I am sharing my screen at the moment.
What? Weird.
No.
It's telling me. Okay. Zoom, come on.
Something's happening. Yeah.
Something's happening.
Okay, right then. Let me now move a few of these addresses over.
Okay, let's try this again. Hmm.
Okay, so there's about 20 of you should now all have access to the labs. So if you log in and click View My Labs, you should now have access. If you don't, then please do let me know. I'm just having a look. There's a few more people still adding usernames onto that list, so there's a few more that I'll copy over. Someone from Bristol, excellent. Everyone who's filled in that form has got access now. So So the lab has been kind of fully tested. Nice lens in the background there. Oh, is that someone spotting my my photography equipment in the background?
Oh yeah.
My wife's a photographer, so tend to have quite a lot of nice camera equipment lying around. There's a brand new Canon EOS R there as well.
Oh, it's really, really nice.
I was hoping to get it set up so you could have a really clear image of what I look like and use it as a webcam, but it was far too clear for my comfort. So I went back to the slightly blurry webcam. Okay, so I can see quite a few questions coming in. So where do we start? How would this compare performance and feature-wise to frameworks such as TensorFlow and PyTorch? Okay, that's a good question. So TensorFlow and PyTorch are frameworks for particular type of domain, right? So PyTorch is really, as far as I understand it, like an inference and deep learning kind of framework, and TensorFlow is for tensor operations. So the level of abstraction that you get for TensorFlow is that you express things in terms of tensors. The idea with Flame GPU is to present similar performance, but by using an abstraction which is around the idea of agents. So what would the performance differences be? Well, probably behind the scenes, if you were to build a complex system simulation in TensorFlow, you'd probably end up with relatively similar performance, assuming that you built the same data parallel algorithms in TensorFlow as we use behind the scenes in Flame GPU. But the level of abstraction that you get would be around tensors and not around agents. So it's about that level of abstraction more than anything else. One of the key ideas really with Flame GPU is to keep that level of abstraction so that you've got a very clean separation between, there we go, now I see it. So that you have a very clean separation between the actual model and the implementation of the simulation. So a lot of models that we come across don't have that. So they have implementation mixed in with the model, and it means that finding problems, debugging issues, and testing and so on becomes much more difficult. Flame GPU2 has about 600 unit tests covering all aspects of the entire library, which means that the simulator itself is well tested, and we have kind of this nice clean separation. So let me see if I can find the next question. So, okay, so GPU, big chunks of data at a time. How do you guarantee order of message passing when messages are delivered simultaneously? Well, we don't. So this is the idea behind having these kind of function layers, is that so if a message should exist, then it will exist by the time that it is read. However, there are no guarantees on the order in which that message will be parsed. But it shouldn't matter, because if you parse through the messages and update your internal state according to what's in the messages, it shouldn't have an impact, particularly on the order, other than potentially some kind of floating point accumulation errors, which may occur and which do occur occasionally. It shouldn't necessarily matter on the order in which they are parsed. There is actually some guarantee of order in the algorithms behind the scenes that we use, but that's not necessarily exposed through the abstraction that you use. You simply use a range-based for loop, and it gives you all the messages that are available for that particular messaging technique. So Jan says, is it possible to run on the CPU, e.g. a Flame GPU can't find a GPU or required libraries? So at the moment, Flame GPU is just on the GPU. We absolutely will be able to support running Flame GPU on the CPU as well. That's not very difficult to do. The difficult part is how you go about balancing some things which should run on a CPU and some things which should run on a GPU. It's a much more difficult task, and it's not a trivial task to solve, because it depends on the it depends on the model, and it depends on the size of the simulation. So it's a dynamic task and requires kind of dynamic scheduling to put things in the right place. But yeah, there's no reason why we couldn't have like a CPU fallback version. There is an original version of Flame. So before even Flame GPU, there is a library just called Flame, which is based off the same principles as Flame GPU. Its implementation differs slightly, but that is targeted at CPU architectures and also for MPI type environments. It tends to be that it has a slightly different use case. So Flame GPU is very good for lots and lots of relatively simple agents in a system, whereas Flame CPU is very good for what I call fat agents, which are incredibly complicated, large agents where you've got relatively few of them. So if you needed to store, for example, gigabytes of information inside a single agent, it wouldn't be a good fit for the GPU, but it would be a good fit for the original Flame CPU libraries. A message is consumed when read, or does an agent subscribe to a bulletin board? Yes, so the messages are essentially stored in a message list. So once they're output, they will be stored in that bulletin board until the end of that iteration. So once you reach the end of an iteration, the message boards are cleared, but reading the message doesn't consume it. It's just, and multiple agents may read the same message. Multiple agents may contribute to the message boards by outputting at different points in that iteration, different messages. So can we export to other formats such as JSON? Well, in Flame GPU 1, the answer was no. In Flame GPU 2, the answer is almost, in that it's on our development tracker as one of the next things to be implemented and will be included before we get to the alpha release in probably 2 or 3 weeks' time. So I guess the long answer to that is yes. Is it possible to install on our own machines and alternatively to using the instance of cloud thing? It is. Let me, I wouldn't necessarily recommend it at this point because it is still kind of very early. We are still actively developing, but if you desperately want to, then you can. So I think, let me just find the right link. So it's, the actual tutorial is on, I'm going to send that on the chat now. So the actual tutorial is on GitHub. It contains like a checkpointed version of our current master development branch from Flame GPU 2. Bear in mind that that is being updated over the next few weeks as we kind of reach that release point. So don't rely on it in the tutorial kind of repo kind of entirely at the moment. But yeah, if you wanted to check that out, you can. You need to have CMake installed, and CMake will bring in all of the dependencies. So one of the nice things with Flame GPU 2 is we've done quite a bit behind the scenes on the infrastructure of building. Flame GPU 1 has very few dependencies. Flame GPU 2 tends to use a lot more kind of existing libraries, but CMake resolves a lot of those and helps that build process to be as simple as possible. Also means that we can target Linux and Windows without having to hard code things like CUDA versions, which we previously had to do. A colleague from our lab wants to join the tutorial, but it's finding it hard to get in. Can someone please let him in? Has he completed the form? Would be my question. Just have a look, see if there's any more names come in. Yes, so there's a few more names come in, so let me just add those. So one more added there, and I think there's one more that I've missed. Okay, excellent. So that's 2 more people added on. If they're still having problems, then please do either put your hand up shout out, turn your microphone on and shout out, or I'll let Juniper know. Where were we on the list? Let me have a look. I didn't catch all the URLs, so I think I've shared those now. Thank you for the overview of Flame. I've read about it, it's good to hear more. Unfortunately, I have a meeting, I have to go. Because I've explained that you can access the session throughout the conference, and yeah, feel free to kind of get in touch with me on Slack if you need any help with that. Can't see anything right now, but the tutorial page has the links. Okay, yes, that's. So we're going to run Flame GPU on the GPUs and those digital cameras as well. Maybe save that for next year, next year's challenge. Run on digital cameras. Okay, so I think that's most of the questions then that have been asked. If you do have any more questions, please feel free to kind of fire those on the chat or speak up. I'd love to chat to some of you kind of one-to-one as well. So if you're, once you've kind of started on your the tutorial exercise, feel free to kind of stick your hand up if you'd like to have a chat with me on that, and we'll kind of just we'll jump into a breakout room so we can have a bit more of a private discussion. It'd be great to find out what some of you are doing, whether or not Flame GPU is going to be useful for your research. Now is a good time to tell us, because it is still under active development, and we are planning a number of releases this year, a number of new features. So if there are features that people need, now's a good time to ask for them. See, someone else has just filled in the form, so bear with me and I'll just add you on as well. And I'd love some feedback as well on what you think of it. So once you've had a chance to have a read through and have a play with the code, run the model, perhaps even kind of have a tinker and put some of your own code in there, I'd love to hear what you think about the process, particularly those who have used Flame GPU 1, whether or not you find it more intuitive, more accessible, what you like, what you dislike. We have moved all of the tutorial information now into a single notebook, so there's no longer like a PDF file which you need to keep reading. It's all contained in one place. I hope is a little bit easier to navigate. So how well does Flame GPU support agent learning? So say each agent shall have a neural network-based controller. So it doesn't have, so Flame GPU doesn't place any constraints on what the behavior of an agent does. Yeah, so if you need an agent that has some kind of learning mechanism, whether that be a neural network or whether it be anything else, you can implement that as long as you can implement it as a collection of variables. Obviously, with a neural network, that may be a collection of array type variables to represent the different layers of your network, and functions, which would be behaviors that operate on those individual variables. So if you wanted to implement neural network-based learning, you could do that within an agent function, but it doesn't have like any template, if you like, as to particular behavior. And each agent have a different range of interactions with others. Yes, so the way in which this is done is it's done via the messages. So take a location message in our kind of simple circles example. There are two different implementations of that model. One is brute force, and in the brute force model, everything considers everything else. So every agent considers every location message, and in fact, it does a distance check as it parses through those messages to see whether or not the message is relevant. There's also an implementation we have of that circles model which uses kind of 2 or 3D spatial interaction. So the difference between that is that there's a data structure built behind the scenes in which we specify the maximum radius in which messages will be returned. Yeah. So if you say, can agents have different range of interactions? They can to an extent. The range of the interaction is controlled by the message type, but if you had an agent variable that specified a particular interaction radius, then you would be able to pass through messages and discard any that were irrelevant to that agent. So if you had, say, a maximum interaction radius, you would set that using spatial, or you would use brute force messaging to consider all, and then the radius value, if it had to be unique to each agent, could be encoded as an agent variable. Your script could respond to agents in that way. So there are a number of different interaction techniques in Flame GPU currently. There's the spatial interaction, there's array messaging, which is effectively a bit like a 2D or 3D chessboard. Some of the other messaging types which are kind of being implemented in Flame GPU 1 and are being ported over are things like network-based messaging. So you can interact with agents that form a network, or interact with agents that exist within a network. So something like a road network example, or a social media network. Yeah, so the environment doesn't, the environment is kind of passive. So the environment doesn't know anything about agents. Agents have to read kind of information from the environment. So an agent needs to know what its location is, absolutely. So it's quite frequent in some of the Flame models that we combine different agent types. So for example, we may have continuous valued agents moving around. So these could be people moving around an environment, and they quite often can interact with other types of agents. So perhaps an array-based agent that represents some discretized part of the environment. That's quite common for things like a pedestrian simulation model. So if we have, for example, navigation vector fields, then what we would do is we would take an area in which people are going to walk around, we discretize that into like this chessboard type layout, and then within that, within each of those cells, we may encode various different velocity forces that represent velocities pointing to particular exits in the model, for example. So we can build a vector field and encode that as agents. Even if that is passive in terms of not updating itself, we can represent kind of a much more complicated environment as an agent. Again, to communicate with other agents, it still has to do that via messages. So our kind of grid cells would output information representing the velocities that they hold, and agents would be able to then query those velocities and update their behaviors accordingly. The advantage of that is that the environment doesn't necessarily have to be passive. The environment could query, for example, the pedestrians that are moving around on top of it, and update its internal representation as well. Yes, so presumably this means that different agents could have different spatial structures. Absolutely. It's one of the key kind of things that we do is have different agents with different spatial structures, and different continuous valued agents can interact with discretized agents. Discretized agents can interact with spatial agents, networks. So agents may be on things like a network. That network may be over the top of some more continuous space. Yeah, they can kind of freely interact with each other. The common things will be that certain message types require information. So if we would like to interact with a spatial message, the agent has to know about what its location is so that it can query from a particular point in space. How can I make custom visualizations for a given model? Is it required to know CUDA in order to make my own visualization? Could you provide a tutorial on how to achieve this? So it's a good question. The difficulty with doing tutorials for visualization is that doing remote visualization is actually incredibly difficult. So you can do things like visualization in a notebook, but all of that is rendered at the host side rather than on the remote side. And with our simulations existing on a kind of a remote GPU, having them render on a remote GPU and then kind of visualize them is actually quite, much more difficult than you would imagine it to be. I would love to be able to do that, and I'm continually exploring new technologies in order to do that. The only way that I know at the moment is via kind of screen sharing, so running a full Ubuntu stack on a remote box and operating that way, which is possible and perhaps something that we'll look at for the future. So with FlameGPU on custom visualizations meant that you had to kind of write all of your own OpenGL code. With FlameGPU 2, we have a simple visualizer which allows you to configure a visualization. So by default, if you create a visualization, all the agents will be rendered in the same way. But what you can do with the new FlameGPU2 visualizer is you can configure say things like the representation of an agent. So if you don't want it to appear as a sphere, you can change the underlying polygon model. If you need it to do certain things like displace it in certain directions, if you need to add another 3D object model to the scene, you can do those things without having to write a lot of OpenGL code or without having to interface into the CUDA part of FlameGPU2. Of course, if you want to do that, then you can get pointers to the raw kind of data, but yeah, the visualization object that we have should allow you to configure visualization much more easily than the original kind of FlameGPU. So the remote visualization problem is entirely worked around by installing locally. I absolutely agree, but the issue with installing locally for a tutorial is, so let me send you that link again. The issue with installing locally is it requires that everybody has a GPU, and that's not always the case, unfortunately. So FlameGPU is only available on NVIDIA GPUs. Let me, for some reason I can't seem to copy that, bear with me a second. So broadly speaking, what are the types of agent-based systems for which GPU performance is expected to be subpar compared to CPUs? Assuming I already have a multi-threaded program, how can I go about deciding whether porting it to a GPU-based computing framework will be advantageous? So that's a great question. FlameGPU is good targeting systems where you have lots of relatively simple agents. Yeah, so lots of relatively simple agents. So the mapping that takes place is that every agent in FlameGPU is represented by a single GPU thread. To keep a very modern GPU device busy, you need, tens to hundreds of thousands of active threads on the device. Yeah, so if your model is, say, a large pedestrian model with tens to hundreds of thousands of people moving around, then that's a good choice for the GPU. If your model is, say, of a complex banking system where you have, say, 10 complex banks that have very large memory requirements, and then that would be a bad choice for the GPU, and much better suited to CPU. So that kind of covers the choice in terms of what's FlameGPU good for. I guess the other kind of part to that is that FlameGPU is good for where we have an appropriate messaging type. So if you need a new type of agent communication that doesn't have an appropriate data structure to accelerate it, then it's possibly going to be slightly slower than a kind of a fine-tuned implementation on OpenMP. Brute force will kind of handle, is kind of a default for anything that's not covered by one of the other types of communication. But obviously there's a cost to having a brute force communication, especially as the population sizes grow. So if you already have a multi-threaded program, how can you go about deciding whether porting it to a GPU-based computer framework would be advantageous? Well, if you've got a relatively simple model and your kind of computational requirements are quite modest, then it may be that you don't need to port it to a GPU. And I wouldn't say necessarily move it to the GPU just for the sake of it. You know, the Flame GPU is designed for performance, kind of critical agent-based simulations, and for large-scale simulations. So don't move it just for the sake of it. Move it if you have a need to get performance and scale. Quite often when we work with collaborators with Flame GPU, we find that people quite like prototyping models in Python, and then leave us to implement kind of the model when it needs to be rolled out and deployed at scale. Part of the kind of the key of Flame GPU2 is that actually we can now develop models in Python, which means that doesn't have to be a completely separate step. We can kind of now hopefully collaborate on simple simple models, translate them directly through to the GPU relatively easily. So hopefully that answers your question. How long are 300 iterations supposed to take in a tutorial? It's taken a while the second time after I adjusted parameters and changed the prey population size. Okay, so what you may find is if you change the condition, or if you change the properties in certain ways, then it may have quite disastrous consequences, right? So if you say increase the birth rate, and there are no predators to kind of eat the prey, then what you may find is that your initial population of, say, 1,000 agents can very quickly escalate population sizes of many hundreds of thousands, if not millions, if there's nothing there to control that. So if your simulation's taking quite a while, it could be that your parameters have allowed for kind of exponential growth. Would be my, it's nothing to do with Instance Hub being heavily loaded. So Instance Hub is just a gateway for pointing you at a cloud-based resource. So all of you that are running the tutorial have got your own cloud-based GPU box, which is dedicated to you. So it will only slow down if you slow it down individually. Yeah, Matt, you've kind of answered my question as well.
Yeah, I was trying to address them while you're talking. Another thing that might be worth mentioning here is obviously Paul mentioned the kind of host side step functions earlier, which could be used to kind of gather statistics about stuff at the end of an iteration. So this would be a good example maybe of where we could have used one of those to keep track of the population numbers. And if we find that they're growing too much at the end of an iteration, then maybe you could give some indication of that, you know, to say, oh yeah, it looks like it's, you know, growing exponentially. And that would give you some kind of indication. So it could be something we could add. Yeah, it kind of demonstrates another use for them.
How do I view the PNG produced in the tutorial?
Yeah, so we sorted that as well, I think.
Sorted that one, excellent. Oh, you're working faster than I am, Matt.
Parallel, isn't it?
Yeah.
What GPUs for.
Is there a way to shuffle data between CPU and GPU such that when needing to do some complicated periodic environment update? Not sure what you mean by that. I'm not sure what you mean by that, Jory. Shuffle the data. Are you able to?
Hi, Paul.
Oh, yes, hi there.
Great tutorial.
Thank
yeah,
you.
I was thinking of more like environments where perhaps you need to read in some data from an external source and then change something of the environmental conditions partway through simulation.
Yeah, so with the so there's a number of ways that you can do this then. So with the API being kind of completely so with Flame being completely API based now, you can kind of implement arbitrary code. So you can read in a file and use that to configure the environment initially. And if that needs to change during simulation, then there are key points that you can do that. So you can implement either a step function, and a step function goes into the function layers just as an agent function would, but it occurs at the end of that simulation step. Yeah, so we use step functions in the context of this tutorial model for logging the population counts into a CSV file so that we can kind of plot the results at the end. But that could, for example, use the host API to modify the environment variables. So at the end of the simulation step, you could modify the environment variable. It could be that what you do is you need to perform some statistics on, say, the populations in order to influence what that variable would be. And again, the host API has functionality to be able to do this. So you can reduce particular agent variables, you can get agent population counts, and then you can set that environment variable. You could, if you really wanted, insert a host function at any point within that kind of simulation, within those simulation layers as well. Obviously, if you put a host function in partway through the agent functions, then you'd have to be aware of the fact that if you change that environment variable, it would be different for any function that would occur after the point that that host function had been kind of executed. But that would also be possible as well.
Excellent, thank you.
That's no problem. Yes, is it possible to implement a basic genetic program with agent gene variables represented as arrays? Absolutely it is. If we'd had a little bit more time, our tutorial example would have been updated to be an ALife example, which would do exactly that. We haven't had enough time. So unfortunately, it's still the Predator Prey example in this tutorial. But no, absolutely, your agent variable arrays could be representing genetic programs. Your behaviors could be modifying those gene variables. Yeah. Trying to find a set of parameters that results in the simulation actually ending. Yeah, that can be quite tricky with the Predator Prey model. It's difficult to kind of find that balance of kind of getting competing agents so that you produce nice oscillating behaviors. So one of the things that we have one of the things that we've done and explored is the ability to run simultaneous simulations and use things like GAs to find interesting areas of parameter space. While it's not officially supported yet within Flame GPU2, the plan after the alpha release is to support simultaneous simulations running on the device. So if, for example, you have a smaller simulation of, say, 100 or 1,000 agents, but what you need to do is do some statistics or parameter exploration, then you'd be able to launch many versions of that same simulation with slightly differing, say, environment properties or slightly different randomized seeds so that you could do some inference on it. And that's certainly something that's in the pipeline and something that we need, in fact, for some of the projects that we're currently engaged with. I do have a PhD student who's in fact used this model to do exactly that. He's had to drive this externally rather than via the new kind of Flame GPU2 interface, but he's devised a cost function that evaluates the quality of oscillating populations to look for interesting areas with this model.
Yeah, again, I think if we'd had any more time, this probably would have been, one of the next things I would have added in.
Yeah.
Because I had the same experience while I was testing it.
Yes, absolutely. Yeah, it is a bit of a random search to find the right parameters. Oscillation is difficult, collapse or explosions. Absolutely, it is. Yeah, it's quite a bit of fine tuning. The key with the tutorial is I want you to kind of not necessarily to get the model to work beautifully. It's more about the interface of how you define your model and how you go about changing parameters of a model so that you're aware of how to run things on the GPU device. Cheap way to make the predators win is to make the interaction radius infinity, so they eat everything. Yeah, it's cheating a bit, but yes, I agree.
Yeah, I would just add, I don't feel like you have to keep going at that until you get it oscillating. If you want to move on and explore a bit more of the, the Flame API and things like that, feel free to. If you feel like you've understood, the point of the exercise really is just to get you playing with the parameters and kind of see what it does. So yeah, move on if you want to get into some more complicated stuff.
It's a great question for everyone. What's your favourite way to visualize and communicate results? Videos, averages, confidence intervals? I'd love to hear what other people's views of that are. With Flame GPU, we've found that having kind of a 3D visualization is quite persuasive, particularly if it's large numbers of agents moving around. From the scientific point of view, it's not as kind of interesting because you're visualizing obviously just a single run of the model, but it's very persuasive in terms of explaining behavior and people can visually see what those behaviors are and what's happening. For our kind of more scientific outputs, these tends to be kind of more statistical outputs of, say, population counts over time with confidence intervals based off different random seeds. What's the Jupyter equivalent of kill? Yes, there we go. Thanks, Mark. Yeah, Peter agrees. Visualizing single runs can be useful for building intuition. Yeah, useful also for kind of debugging models as well. If you run something and see that some agent randomly disappears off in a direction, it's a nice visual way of validating your model. How are people getting on with virtual cloud instances? I can see there's quite a few people running Great. There's a few comments coming from my developer. Oh, there's Peter Hayward, I see. So he works in part of my team. So suggesting that what we could do for the simulation is add what's called an exit condition. So this is a host-based function that allows you to use the host API to query properties of the simulation. So we could, for example, check if a population size goes above a particular value, we could exit the simulation early. So we could, in effect, detect that exponential growth and stop the simulation early. So someone asking about reference to CUDA compute capability. So I suspect that the documentation you're looking at is for the original Flame GPU, which is quite old. So double data type has been available since compute capability kind of 2. And I think that is long since depreciated. So any device that you get will have double support. Where compute capability gets a bit more interesting is that there are certain kind of cutting edge features that we may utilize for certain implementations of certain message interactions, for example. And it could be that we end up with some specialization of code for certain compute types in our code base, but that will be transparent to you as a user. I forget what the minimum compute version is that we support. In fact, Pete said compute SM35 and above, which is very old actually, SM35. So we pretty much run on any NVIDIA GPU. Excuse me for just one moment. Oh, well, I'm back again. They're not actually instance hubs GPUs, so it relies on AWS in the background. So I don't mind if you set one on fire. That's fine. I don't think they build for that. So we've got about 5 minutes left of tutorial. Please do feel free to continue to kind of play with that example on Instance Hub. Do be aware that when that time limit runs out on the Instance Hub page, the instance will shut down and everything will disappear. So it's not a, there's no persistent storage. Once it shuts down, everything's gone. So what you can do within the notebook state is you can save the notebook state, or if you open up the main.cu file, you can save that locally if you wish, and then kind of re-import it next time you kind of want to have a play with it. Tutorial experience is great. Thinking about our own future tutorials when we get started with Instance Hub, it's not obvious. No, it's not obvious. So Instance Hub is something which I've developed myself to solve a very particular problem, which is kind of getting GPUs into the hands of people when you want to run training or tutorials, but without having, but it also provides some kind of constraint on spend, which is the biggest problem with something like AWS. It's very easy to run up an extremely large bill if sessions are not kind of automatically shut down. So Instance Hub allows me to take care of that. I want to make it publicly available, but I'm slightly terrified of the liability implications of doing so, because we have to store people's AWS keys. So I haven't made it publicly available for fear of being sued to oblivion by someone should we be hacked or something like that. What I can do is I can make it accessible to people who, on a kind of a one-to-one basis. If you desperately need it, you can contact me and I will explain what the conditions of its use are, namely that you monitor your own AWS account, don't leave keys on the website that are unused, and so on. I do have some ideas about how I can make that a little bit more secure without actually fully storing keys. So perhaps at some point in the near future, I will find some time, I don't know quite how that will happen, but I'll find some time to be able to make those updates and push that out. I know that NVIDIA are potentially quite keen on using it as part of their Deep Learning Institute experience. So feel free to get in touch with me personally, Jory, if it's something that you'd like to have a play with. So yeah, so using GAs to look for interesting dynamics and explore models. Can we say how we do that? So currently, how we do that is in the original Flame GPU. Is that we have an external Python script that effectively configures a set of 0.xml models and then procedurally runs through a load of GPU simulations in Flame. For Flame GPU 2, it will be much simpler because you will be able to create multiple instances of a CUDA agent model. So you can take a model, create, modify the environment, create a new CUDA agent model, and queue all of those things up so that eventually you'll be able to say like model ensemble.simulate, and it will run a whole load of models rather than just one. And then obviously at the end of that process, you're free to kind of implement whatever heuristic technique you would like for searching, which is obviously much simpler if we have Python bindings where you have access to things like scikit-learn for doing that. Once that feature is kind of enabled in the framework, we will put an example, just as we have with Flame GPU ones full of examples for different cases. We'll put a modeling example on how to do a simple GA search as part of the downloadable examples that you can get. Thank you very much for attending. It's a shame we can't be in Canada. I was quite looking forward to that. But it's great to see so many people participating virtually. I think that takes us up to our time limit, actually. So for those that want to continue, please feel free. I am on Slack for the rest of the week. So if you've got any questions or you need some help with the tutorial, then please do reach out to me, get in touch. Happy to answer any questions, happy to receive any feedback on the tutorial, happy to receive any feedback on Flame GPU. Would really appreciate that. Cheers, everyone. Thank you also to Matt. You spent an incredible amount of time putting all of this together over the last week or so.
Only because it took me much longer than it should have done.
All right, thank you both. I might close this meeting room as I hear the other chairs getting started in lecture hall A for some updates before the keynotes. So thank you very much, Paul and Matt.
Absolutely no problem. Pleasure as always. Thank you very much, Odds. Goodbye to everyone then.
Bye.
Cheers.